Fuse-blown fuse indicating features are commonly used to indicate when a fuse has blown, providing a visual indication for quick troubleshooting. However, these features may not always activate as quickly as some downstream devices such as variable frequency drives, also known as VFD, and fast circuit breakers. The ID feature may not be activated if a fuse blows on a device that can shut off very quickly. This is because the ID indicator is in parallel with the fuse element, and the downstream device shutting off can create a very high impedance that prevents the indicator from tripping. This limitation can result in the following. Firstly, delayed troubleshooting. The lack of an ID indication may delay troubleshooting efforts, as the fuse may not be immediately identified as the cause of a circuit failure. Secondly, false readings. The high impedance of the untripped ID indicator can make it appear that the device terminals are still receiving voltage, even though the fuse is blown. Thirdly, safety hazards. In critical applications, the failure to indicate a blown fuse can pose safety risks. The following devices are known to be susceptible to this limitation: variable frequency drives, fast circuit breakers, and other devices with very fast shutdown speeds. To mitigate this limitation, consider the following strategies. 1. Use alternate fuse types. Consider using fuses with other indicating mechanisms, such as LED indicators or external indicators. 2. Enable monitoring circuits. Implement monitoring circuits that can detect blown fuses and provide external indications. 3. Conduct thorough inspections. Regularly inspect fuses and check for any signs of damage or failure, even if the ID indicator is not activated. While ID features provide a convenient way to identify blown fuses, it is important to be aware of their limitations. By understanding the potential for delayed or missed indications with certain downstream devices, appropriate mitigation strategies can be implemented to ensure accurate troubleshooting and minimize safety risks. Let's delve deeper into the nuances of blown fuse indicating features and their behavior with fast-acting devices. We will explore the underlying electrical principles and practical steps to address these limitations. Fuses are designed to protect electrical circuits from overcurrent conditions. When the current exceeds the fuse's rated capacity, the fuse element melts, interrupting the circuit and preventing damage to downstream components. The blown fuse indicating feature provides a visual signal when this occurs, typically through a small indicator that changes color or illuminates. This indicator is usually connected in parallel with the fuse element. Under normal operating conditions, the fuse element provides a low impedance path, and very little current flows through the indicator. However, when the fuse blows, the fuse element opens, and the indicator becomes the primary path for current flow. If the current is sufficient, the indicator will activate, signaling the blown fuse. The issue arises when a downstream device, such as a VFD or a fast circuit breaker, can shut off the circuit very quickly after the fuse blows. In these scenarios, the voltage across the fuse may drop rapidly, preventing enough current from flowing through the indicator to activate it. The high impedance of the untripped indicator can then create a false reading, making it appear as if voltage is still present at the device terminals. Variable frequency drives are used to control the speed of electric motors by varying the frequency and voltage supplied to the motor. They often incorporate sophisticated protection mechanisms that can quickly shut down the drive in response to various fault conditions, including overcurrents. Similarly, fast circuit breakers are designed to trip very quickly in response to overcurrents, minimizing the duration of the fault and protecting sensitive equipment. When a fuse blows in a circuit protected by one of these devices, the device may shut off the circuit before the fuse indicator has a chance to activate. This can lead to confusion and delays in troubleshooting, as technicians may not immediately realize that a fuse has blown. To address this issue, it is important to understand the electrical characteristics of the fuse, the indicator, and the downstream device. The impedance of the indicator plays a crucial role in determining whether it will activate before the circuit shuts down. A higher impedance indicator will require more voltage to activate, while a lower impedance indicator will activate more readily. The shutdown speed of the downstream device also affects the indicator's activation. A faster shutdown speed will reduce the time available for the indicator to activate, increasing the likelihood of a missed indication. There are several strategies that can be employed to mitigate these limitations. Firstly, consider using fuses with alternate indicating mechanisms. Some fuses incorporate LED indicators that are more sensitive and can activate more quickly than traditional indicators. Others use external indicators that are connected to the fuse through a separate circuit, providing a more reliable indication of a blown fuse. Secondly, implement monitoring circuits that can detect blown fuses and provide external indications. These circuits can be designed to monitor the voltage across the fuse or the current flowing through the circuit, providing an independent indication of a blown fuse, regardless of the indicator's activation. Thirdly, conduct thorough inspections of fuses regularly, even if the indicator is not activated. Look for any signs of damage or failure, such as discoloration or cracks in the fuse body. If there is any doubt about the condition of a fuse, it should be replaced. In addition to these strategies, it is important to carefully select fuses that are appropriate for the specific application. Consider the fuse's voltage rating, current rating, and interrupting rating, as well as its speed of response. A fuse that is too slow may not protect the circuit adequately, while a fuse that is too fast may nuisance trip. It is also important to ensure that the fuse is properly installed and maintained. Check the fuse holder for any signs of corrosion or damage, and replace it if necessary. Ensure that the fuse is securely seated in the holder and that the contacts are clean and tight. By understanding the limitations of blown fuse indicating features and implementing appropriate mitigation strategies, it is possible to ensure accurate troubleshooting and minimize safety risks. Remember to always follow proper safety procedures when working with electrical equipment. Wear appropriate personal protective equipment such as gloves and safety glasses, and energize the circuit before working on it. If you are not qualified to work on electrical equipment, consult a qualified electrician. Furthermore, understanding the specific characteristics of different fuse types and their applications is crucial for ensuring effective circuit protection. Fuses are broadly categorized into different types based on their construction, operating characteristics, and intended use. Some common types include cartridge fuses, blade fuses, and semiconductor fuses. Cartridge fuses are cylindrical fuses that are commonly used in residential, commercial, and industrial applications. They are available in a wide range of voltage and current ratings and are typically used to protect general-purpose circuits. Blade fuses, also known as plug-in fuses, are commonly used in automotive applications. They are characterized by their flat blade-like terminals and are designed to be easily replaced. Semiconductor fuses are specialized fuses that are designed to protect sensitive semiconductor devices, such as diodes and transistors. They are characterized by their fast response times and are typically used in electronic equipment and power supplies. In addition to these general types, fuses are also classified based on their operating characteristics, such as their speed of response. Some fuses are designed to trip quickly in response to overcurrents, while others are designed to trip more slowly. Fast-acting fuses, also known as quick-blow fuses, are used to protect sensitive electronic equipment that can be damaged by even brief overcurrents. Time delay fuses, also known as slow-blow fuses, are used to protect circuits that experience temporary overcurrents, such as motor starting circuits. When selecting a fuse, it is important to consider the specific requirements of the application. Choose a fuse that is appropriate for the voltage and current ratings of the circuit, as well as the type of load being protected. It is also important to consider the fuse's speed of response and its interrupting rating. The interrupting rating is the maximum current that the fuse can safely interrupt without rupturing or causing damage to the surrounding equipment. It is important to choose a fuse with an interrupting rating that is sufficient for the potential fault current in the circuit. In addition to selecting the appropriate fuse type and rating, it is also important to ensure that the fuse is properly installed and maintained. Use the correct fuse holder for the fuse type being used, and ensure that the fuse is securely seated in the holder. Check the fuse holder for any signs of corrosion or damage, and replace it if necessary. Regularly inspect fuses for any signs of damage or failure, such as discoloration or cracks in the fuse body. If there is any doubt about the condition of a fuse, it should be replaced. By understanding the different types of fuses and their applications, and by following proper installation and maintenance procedures, it is possible to ensure effective circuit protection and minimize the risk of electrical hazards. And remember, safety should always be the top priority when working with electrical equipment. Always de-energize the circuit before working on it, and wear appropriate personal protective equipment. If you are not qualified to work on electrical equipment, consult a qualified electrician. Let's further explore the implications of the high impedance of an untripped fuse indicator in circuits with fast-acting devices. When a fuse blows, the voltage across the fuse element should theoretically drop to zero. However, the presence of the untripped indicator in parallel with the fuse element creates a parallel circuit. This parallel circuit consists of the high impedance of the indicator and the impedance of the downstream device. The total impedance of this parallel circuit can be significant, especially if the downstream device has a high impedance. As a result, the voltage across the fuse may not drop to zero immediately. Instead, a residual voltage may remain across the fuse, which can be misleading. This residual voltage can be misinterpreted as an indication that the fuse is still intact and that the circuit is still energized. This can lead to dangerous situations, especially if someone attempts to work on the circuit without first verifying that it is energized. The high impedance of the untripped indicator can also affect the operation of other components in the circuit. For example, it can cause voltage drops across other components which can affect their performance. It can also create noise in the circuit, which can interfere with the operation of sensitive electronic equipment. To minimize the effects of the high impedance of an untripped indicator, it is important to choose indicators with low impedance. Low impedance indicators will allow more current to flow through them, which will help to activate them more quickly. It is also important to ensure that the downstream device has a low impedance. This will help to reduce the total impedance of the parallel circuit and minimize the residual voltage across the fuse. In addition to these measures, it is also important to use proper grounding techniques. Proper grounding will help to reduce noise in the circuit and minimize the risk of electrical shock. It is also important to follow all applicable electrical codes and standards. These codes and standards are designed to ensure the safety of electrical installations and to minimize the risk of electrical hazards. By understanding the implications of the high impedance of an untripped fuse indicator and by taking appropriate measures to mitigate its effects, it is possible to improve the safety and reliability of electrical circuits. Always remember to prioritize safety when working with electrical equipment. If you are not qualified to work on electrical equipment, consult a qualified electrician. Now, let's consider some real-world scenarios where the limitations of fuse-blown fuse indicating features can have significant consequences. Imagine a critical industrial process that relies on a variable frequency drive to control the speed of a motor. If a fuse blows in the VFD circuit, the process could be interrupted, resulting in lost production and potential financial losses. If the fuse indicator fails to activate due to the fast shutdown of the VFD, technicians may spend valuable time troubleshooting other components before realizing that a fuse has blown. This delay can prolong the downtime and increase the associated costs. In another scenario, consider a medical device that relies on a fast circuit breaker to protect sensitive electronic components. If a fuse blows in the device circuit, the circuit breaker may trip before the fuse indicator has a chance to activate. This can lead to a malfunction of the medical device, potentially jeopardizing patient safety. The lack of a clear indication of the blown fuse can further complicate the troubleshooting process, delaying the repair and increasing the risk of a recurrence. These examples illustrate the importance of understanding the limitations of fuse-blown fuse indicating features and implementing appropriate mitigation strategies. By using alternate fuse types, enabling monitoring circuits, and conducting thorough inspections, it is possible to minimize the risk of missed indications and ensure accurate troubleshooting. It is also important to educate technicians and maintenance personnel about these limitations and the proper procedures for identifying and replacing blown fuses. Regular training and awareness programs can help to prevent errors and ensure that electrical systems are properly maintained. In addition to the technical aspects, It is also important to consider the human factors involved in troubleshooting electrical circuits. Technicians may be under pressure to quickly diagnose and repair faults, which can lead to mistakes and oversights. It is important to create a culture of safety and encourage technicians to take their time and follow proper procedures. Providing clear and concise documentation can also help to prevent errors and ensure that troubleshooting is performed effectively. The documentation should include information about the fuse types used in the circuit, their ratings, and the location of fuse holders. It should also include instructions on how to properly inspect and replace fuses. By combining technical expertise with human factors considerations, it is possible to create a more robust and reliable electrical system. Remember, electrical safety is everyone's responsibility. By working together and following proper procedures, it is possible to prevent accidents and ensure the safety of workers and the public. And finally, let's discuss the future trends in fuse technology and their potential impact on blown fuse indicating features. Fuse manufacturers are constantly developing new and improved fuse designs that offer enhanced performance and reliability. Some of these advancements include the use of new materials, improved construction techniques, and integrated electronic monitoring capabilities. One trend is the development of smart fuses that can communicate their status to a central monitoring system. These fuses can provide real-time information about their voltage, current, and temperature, as well as their blown fuse status. This information can be used to improve the efficiency of maintenance operations and to prevent equipment failures. Another trend is the development of self-resetting fuses that can automatically restore power to the circuit after a fault condition has been cleared. These fuses can help to reduce downtime and improve the reliability of critical systems. As fuse technology continues to evolve, it is likely that blown fuse indicating features will become more sophisticated and reliable. New types of indicators may be developed that are more sensitive and can activate more quickly. Integrated electronic monitoring capabilities may also be incorporated into fuses, providing more comprehensive information about their status. These advancements will help to improve the safety and reliability of electrical systems and to minimize the risk of electrical hazards. However, it is important to remember that even the most advanced fuse technology is not foolproof. It is still essential to follow proper installation and maintenance procedures and to conduct regular inspections of fuses and electrical equipment. By combining the latest technology with sound engineering practices, it is possible to create a truly safe and reliable electrical system.